Let me start this lecture on magnetic vector potential. We previously defined magnetic induction from Lorentz force equation. We proved and discussed Gauss' law of magnetostatics and Maxwell's second equation of electrodynamics, which says that magnetic monopoles or charges are not there and are not physical reality. We then, in lecture 3a, dealt with a law enunciated by Biot and Savart, whose form in the case of filamentary current distribution is this one, and in the case of volume current distribution is this one. Now they are equivalent descriptions of a current distribution. One logical thing to ask is that whether these laws are consistent. That is, are these laws telling the same thing? B here in Maxwell's second equation is solenoidal, and Biot-Savart's law specifies the form of B explicitly. Now this B predicted by Biot-Savart's law cannot be arbitrary, but has to satisfy Maxwell's second equation. That is, this B has to be solenoidal. It has to satisfy Gauss' law of magnetostatics. We wish to verify whether these laws are consistent. So let us start with Biot-Savart's law first. Biot-Savart's law gives us the value of magnetic induction. This is for filamentary distribution, this is for volume current distribution, and let us evaluate divergence of this given B in both the cases. We first consider the filamentary current distribution. So this is the filament under consideration, C prime, and it produces a magnetic induction at the point P, the expression of which is given by Biot-Savart's law. Now let us take divergence. And if we take divergence, we have a divergence sitting over here. Now in this expression we have two operations. One is integration over the source, that is over R prime, and another is taking derivative with respect to the field through the operation called divergence. Now since source coordinate and field coordinate are independent, we can interchange these two operations, and if we do that, we end up with this expression. Now in this expression we first do the integration and then take divergence, but here after this interchange what we do is we take first divergence and then we take integration over source. Now we'll use this vector identity and we can identify P with vector dr prime and Q with r cap by r square. And if we put this expression in the integration, we end up with divergence B consisting of two terms on the right hand side. Now each of the term is 0 because here we have curl of vector dr prime, and dr prime is obviously a source function while curl operates on field, so it is 0. And here r cap by r square can be written as minus grad of 1 by r, and therefore curl grad comes into the scene. Now curl grad is 0 as per vector identity, and therefore both the terms vanish and we end up with divergence B equal to 0, and this result follows from Biot-Savart's law. We now go over to volume current distribution. Now this is a volume current distribution. This is the volume under consideration, and this volume has some current in it which produces a magnetic induction at the point P, and this value of magnetic induction is given by Biot-Savart's law. Now let us take divergence. So divergence sits over here, and a study of this expression shows that here also we have two operations. One is integration over source and the other one is taking divergence with respect to the field coordinate. Now since field coordinate and source coordinate are independent, we can interchange the order of operation, and if we do that, we end up with this expression. Now as before, we can use this vector identity, and if we identify P with J and Q with r cap by r square, we end up with this expression. And when this one is put in the integration, we have divergence B consisting of two terms on the right hand side. Now each term is 0 because of the reason that here vector J is a source function, but it is operated upon by curl, which is a field operator. So this is 0, and here as before we have r cap by r square, which can be expressed as minus grad of 1 by r, and curl grad comes into the picture, which makes it 0. So what we have is divergence B equal to 0, and this result follows from Biot-Savart's law. So we have found out divergence B from Biot-Savart's law, and now let us address these few questions. The first question is find divergence B from Biot-Savart's law, which we have just now done. So this is Biot-Savart's law for filamentary distribution and volume distribution, and from here we have found the value of divergence B to be 0. So this is the answer to question number 1. Now let us go to question number 2, which says that show that Biot-Savart's law and Gauss' law of magnetostatics are consistent. Now Gauss' law of magnetostatics is closed surface integration of B equal to 0. If we apply Gauss divergence theorem, this was discussed in lecture 2a, then we end up with divergence B in the integrand, and we then have divergence B is 0. Now this is Maxwell's second equation of electrodynamics, and this is Gauss' law of magnetostatics. Clearly therefore Biot-Savart's law gives us divergence B equal to 0, and Gauss' law of magnetostatics also gives divergence B equal to 0. So both Biot-Savart's law and Gauss' law of magnetostatics lead to divergence B equal to 0, and hence they are consistent, and this is wanted in question number 2. Next is question number 3, which asks show that Biot-Savart's law gives us a divergenceless B, and this we have done here. This is Biot-Savart's law. From here we got divergence B equal to 0, and this is divergenceless B. We have obtained it from Biot-Savart's law. So we have got the answer to question number 3 also. Question number 4 says that show that Biot-Savart's law leads to Maxwell's second equation of electrodynamics, and this we have done. Biot-Savart's law leads to divergence B equal to 0, which is Maxwell's second equation of electrodynamics, and so this is the answer to question number 4. So we have answered all the questions. All the laws we have stated till now, namely Lorentz force law, the Biot-Savart's law, Ampere's force law, Maxwell's second equation, Gauss' law of magnetostatics, all are trying to describe various aspects, characteristics or features of magnetic induction, and all are tied up at one point, that is B is solenoidal, and it has to be in order to develop a systematic, disciplined theory in a consistent manner. Now to the main topic of today's lecture, definition of magnetic vector potential. Let us recall Gauss' law of magnetostatics, this integral form from which follows Maxwell's second equation of electrodynamics, divergence B equal to 0, which we did in an earlier lecture. Now let us use this vector identity, div curl of any vector equal to 0. So comparison gives us, here we have divergence, here we have divergence, so comparison gives us B equal to curl A. So we have B equal to curl A, where A is defined as magnetic vector potential. Now let us have a relook at the expression of magnetic induction as given by Biot-Savart's law. We see that there are integrations over source quantities. This is a filamentary distribution chosen. So here is integration of our source quantities. So after integration over r prime, there will be no r prime left, which means magnetic induction is a function of field coordinate r. And since B equal to curl A, since B is a field function and curl also operates on field, we expect that vector A will also be a field function. So what we emphasize is B, magnetic induction, and vector A, the magnetic vector potential, both are field functions. Let us now investigate if there is any arbitrariness in the definition of B. That is, if there is any weak point or loopholes or ambiguity in this definition of vector A. Now B equal to curl A is the definition of vector A. The arbitrariness or ambiguity is because of this vector identity, namely curl grad of any scalar equal to 0. We have said that vector A gives magnetic induction vector B. Now let us instead start with this vector A plus grad of gamma, and this we call A prime, and try to evaluate the magnetic induction, which let us call vector B prime. Now if B equal to curl A, then B prime is curl of A prime, so that we can put the value of A prime here, and that gives us curl A, because curl of grad is 0 as per this vector identity. So we see that we get to the same B even if we start with a different vector potential and the two differs by grad of gamma. Actually, it doesn't matter which one you start with. We can start either with A or with A plus grad gamma or with A plus vector C, where C is a constant vector, any constant vector, or with A plus grad of gamma plus vector C. So this is the arbitrariness in the definition of vector A. Taking curl of any one will give us vector B. So this is the arbitrariness or lack of a unique choice or unique value of vector A in finding magnetic induction vector B. So these are the conclusions. Definition of vector A is not unique but arbitrary to the extent of addition of grad of gamma apart from a constant C. Vector A is therefore not a fundamental vector because it has no unique value, so it is not a fundamental vector. Considering a quantity which is itself unsure of its value, sometimes A plus grad gamma, sometimes A plus C, and so on and so forth, cannot be used as a face to represent any system. So vector A cannot be a fundamental vector, but vector B is a fundamental vector. Our aim, our sole goal is to find the value of magnetic induction. One might at this point therefore question that if A is not unique, and it is not, it has various faces, and if A is not fundamental, then what is the need of this choice? What is the role of magnetic vector potential in magnetostatics? Now we'll address this point a little while after. Before addressing this issue, let us find how vector A will look in filamentary and volume current distribution. We have defined vector A from B through B equal to curl A. The expression of B is given by Biot-Savart's law. Similarly, what will be the explicit expression of vector A? We'll try to find that in filamentary current distribution as well as in volume current distribution. First, we'll take up filamentary current distribution. Let us find the expression of vector A, the magnetic vector potential, in case of filamentary current distribution. We start with the defining equation. So curl A is B, and by Biot-Savart's law, let us write down the value of vector B, which involves r cap by r square, which can be written as minus grad of 1 by r because of this relation, and put it back to end up with this expression, and cross products can be reversed at the cost of a negative sign, so we end up with this expression. Now let us use this vector identity and we transpose to end up with this relation. Now identify phi as 1 by r and vector p as vector dr prime, we get this relation. Now here we have a curl of dr prime, which is 0 obviously, because curl operates on field vector r and dr prime is a source quantity. So what we have is this integrand is actually equal to curl of dr prime by r. Now putting this one here, we get this expression. Again here we have two operations. One is curl, which is with respect to field, and the other one is integration over source, and they can be interchanged because r and r prime are independent, and then we end up with this relation where curl has gone outside. So properly written, curl A becomes curl of this thing. So comparison easily gives this value of vector A, and we can use this expression vector r as r minus r prime, but here scalar r is involved and therefore we have to take its mod, and we have this relation. And clearly here integration is our source, and therefore it turns out that after integration source coordinate will not be present, and therefore A becomes a field function. We now switch over to volume current distribution. So we are trying to find the expression of vector A in case of a volume current distribution. As in the previous case, we can start with the definition of vector B equal to curl A. So curl A is B, and instead of B we will use Biot-Savart's law for volume current distribution. So this is it, and instead of r cap by r square we have as before minus grad of 1 by r, which when put here and the cross product put in order, then we end up with this expression. As in the previous case, we can use the same vector identity, and then transposition gives us this line. We can identify 1 by r as phi and j as p to have this line where we have a curl of j, and curl operates on field, j is a source function, so this term is off, and therefore the integrand can be written as curl of j by r. So we can put curl of j by r in the integrand to get this expression. Here too we have two operations. One is curl, which is with respect to field, and the other is integration over source. We can interchange them because r and r prime are independent, and therefore we end up with this expression where curl has come out, curl has gone outside. So we have this expression, and we can compare curl of A with curl of this quantity to end up with the value of vector A. Here too, integration over source quantity means after integration we no longer have source, but we have the field quantity present. So A is a field function. Now we address the question we raised regarding utility or significance of vector A, the magnetic vector potential. We said that our ultimate or only goal is to get vector B, the magnetic induction, to know about magnetic induction for a given current distribution. The magnetic vector potential, which is not unique, which is arbitrary, is not fundamental. But why define vector A then? Let us focus attention to the expression of vector B as given by Biot-Savart's law. It involves complicated integrals, there being 1 by r square, and in the integrand there is a cross product also. So in many problems, evaluation of these integrals will give us a lot of trouble and will be too much time consuming. Instead, let us look at the integrals involved in the expression of magnetic vector potential. They involve just 1 by r and are simpler, greatly simple compared to that of B. Clearly, we can evaluate vector A first by evaluation of these easier integrals and then take curl A to find vector B. Even though it may be a two-step process to find vector B, it is faster and simpler than a one-step evaluation of a difficult integral. So, magnetic vector potential has been introduced to simplify calculations, to make our life simple, though our main focus is definitely on vector B. Now, let us evaluate or focus on the dimension of magnetic vector potential. This we can easily find from the unit and dimension of B. Let us use this definition of vector A, that is B equal to curl of A, which is the defining relation. Now, unit of B is Tesla, unit of grad, which is actually del del x, del del y, del del z, the unit is 1 by meter. So, A has a unit Tesla into meter. Alternately, we discussed in lecture 1a, this combination of unit is Tesla. So, simplification gives us the unit of magnetic vector potential to be Newton per ampere. Another combination of unit for Tesla, as discussed in this lecture, was volt second per meter square, and from here we end up with volt second per meter as the unit of magnetic vector potential. Here one thing we have to be very alert about, and that is this A represents ampere and this A represents magnetic vector potential. Now, about dimension of magnetic vector potential, which can also be obtained through this defining relation. It is extremely easy, you can have a check. Having defined the magnetic vector potential and having found the explicit expression of vector A, we now proceed to check if vector A we are suggesting leads to a justifiable vector B. In physics, what one does is to verify and re-verify and verify once more. We too should develop the mentality to go on verifying what we are doing time and again and from different angles and perspectives. That makes our clear understanding clearer. So, we will assume vector A now and find the expression of magnetic induction. We start with filamentary current distribution. So, let us straight away take B equal to curl A and put this expression down here. And now this expression has two operators. One is integration over source, and this is differentiation or curl with respect to the field. And we can interchange the operations because R and R prime are independent. And if we do that, we end up with this expression. Here we had to perform first integration and then curl, but here we have to take curl first and then perform integration over source. Now, use of this vector identity helps us to identify phi as 1 by r and vector p as dr prime. On the right side we have two terms, one of which vanishes because dr prime is source function while curl is with respect to field, and therefore we are left with just one term on the right hand side. Now, use of grad of 1 by r as minus r cap by r square gives this one, and when we put it back here we end up with the expression of B to be this one, which is the well-known Biot-Savart's law. So what we have done here is we have reproduced Biot-Savart's law starting from this expression of vector A. We now switch over to volume distribution. Now this is the volume distribution of current, and this is the expression of vector A, and let us use the defining relation for B. Let us put A here to end up with this relation. Again we have to perform first integration over source and then curl with respect to field, but we can interchange these operations because R and R prime are independent, and if we interchange the operations we get this relation. Now use of this vector identity gives us this expression. We can identify phi as 1 by R and P as vector J. Now we have two terms on the right hand side, one of which will be 0 because J is a source function and curl is operating over field. So therefore we have only one term on the right hand side. Now let us use this relation to end up with curl of J by R as J cross R cap by R square, which when substituted here gives us the Biot-Savart's law. So again, starting from this expression of A for volume current distribution, what we have got is Biot-Savart's law. We have reproduced Biot-Savart's law. Let us now address a few questions, and here they are. Let us take up the first question. Assume A, that is the magnetic vector potential, and from it we have to find vector B. Now this is what we have done exactly. We started with these expressions of vector A, one for filamentary distribution, one for volume current distribution. We used this defining relation for A, that is B equal to curl A, and we got these expressions for B. So this is answer to question 1. Question 2 says that show that vector A leads to solenoidal B. Now we started with vector A and we got this expression of B, which is actually Biot-Savart's law. In the initial phase of the lecture, we proved that the B given by Biot-Savart's law is indeed solenoidal. So this A leads to a solenoidal vector B. So question 2 has been answered. Next, third question is, which vector A leads to Biot-Savart's law? Obviously this A gives us Biot-Savart's law, so this is answer to question 3. Which A leads to Maxwell's second equation of electrodynamics? Now this A gives us this B, which is Biot-Savart's law, and from here we got divergence B equal to 0, which is actually Maxwell's second equation of electrodynamics. So this is the answer to question 4. Question 5 says that which A leads to Gauss law of magnetostatics? Again, we started with this A and obtained this B, and then we got divergence B 0. Now if we consider the surface integral of B, closed surface integral of B, and use Gauss divergence theorem, then we have a divergence B getting into the integrand, and this divergence B is 0, so this is 0, and this is Gauss law of magnetostatics. So this A leads to Gauss law of magnetostatics. So again, answer is this one, question 5. The sixth question says that what is curl of A and what is its significance? Now curl of A represents magnetic induction, curl of A is B. Magnetic induction represents a current distribution. Again, in a magnetic induction, if we have a charge Q and if it is moving with velocity V, then that charge experiences a Lorentz force. So these are the significance of vector B. So we have answered all the questions. Let us now do a problem. This is the question. A vector potential A has been given where vector A is constant, the small a is constant, and capital A represents magnetic vector potential, vector R is the position vector. Now from here we have to find the magnetic induction. So again, the defining relation, we have to invoke it, B equal to curl of A, put the value of A to end up with this relation. Now we can use this vector identity, curl of A cross R, this leads to 4 terms, and here is that half, and out of these 4 terms, let us check them one by one. The first term involves vector A and a grad here, so obviously this will give us a 0. A dot grad of R, A dot grad can be verified to be Ax del del x, Ay del del y, Az del del z, and that will operate upon R, and this gives us vector A. So the second term actually gives us minus vector A because of this negative sign. The third term is divergence R into vector A. Divergence R is 3. You did it in your mathematical physics class. So divergence A is 3, therefore we have 3A here. And this term is divergence of A being a constant, it is straight away 0. So we have therefore B equal to vector A as the answer. So if we start with A equal to half A cross R as magnetic vector potential, then it generates a magnetic induction of this amount. So here the significance of this A is that this is the magnetic induction. So we can recast it in this way. Also sometimes we write the cross product in this way by bringing a negative sign. It is also a popular way to write. These are popular problems. So we have solved this problem. Let us focus to another problem. The magnetic induction is being wanted corresponding to a current distribution which is described by this value of A, and the points are given where magnetic induction is to be found out. So the starting point is B equal to curl A, and then put the value of A, then curl of A can be written in this way, and if you do it, you can check the calculations, then we end up with this expression of B, and here we have x, y, z, so this is a function of this B is a function of x, y, z. And now we can put the values of x, y, z as given in the question, these 2 points, and if you put it, we get these values as the values of magnetic induction corresponding to this A. We now address a very important topic called gauge transformation for the fields. Here field means E and B. E is electric field, B is magnetic field. We will discuss how we can reach the same fields E and B in spite of starting from different sets of potentials. By potential here we mean the scalar potential corresponding to the electric field and the vector potential corresponding to the magnetic field. Let us first give an example from mechanics. Take the case of a length PQ. Now PQ is invariant and we can measure it by whichever technique we wish to, that is from different frames of reference. Say we can measure it from XY frame, or we can measure it from r theta, that is a rotated frame of reference. Whichever frame we use, the length is same, and shifting from one frame to another, say from XYZ to r theta phi, or from r theta phi to rho phi z, etc., is called transformation. And invariance means even if you transform from one coordinate system to another coordinate system, the length is same, the length remains unaltered, and this is called invariance. Now let us go to what we were referring to. Let us begin with a problem, and this is the problem which says that we have to find the fields, that is electric field and magnetic field, starting from two sets of potentials. So one set is vector A and V, and the other set is related to the former through these equations. So A plus grad of gamma is the new magnetic vector potential, and V minus del del T of gamma is the new scalar potential. Now we have to verify whether these two sets of potentials give the same field. And moving from this set of potential to that set of potential is called gauge transformation. And in spite of this gauge transformation, in spite of this shift, if we find that the fields are same, then we'll call the fields to be gauge invariant. That is, they do not change, they do not alter even if we change our set of potentials, that is frames. Now we start with Maxwell's second equation of electrodynamics, which is divergence B equal to 0, from where, as we defined in this lecture, we come to B equal to curl A. Let us now make use of Maxwell's third equation of electrodynamics, which is curl A equal to minus del B del T. We'll deal with this one, we'll prove this one in a separate series on electromagnetic induction when we will discuss Faraday's law. Now in this lecture we have to accept this equation. Now here we have B, and instead of B we can put curl of A, and therefore we have this relation. Now this equation involves again two operations. One is curl, which is with respect to space, and the other one is time derivative, which is with respect to time. Now since space and time are independent, we can interchange the operations. Now the interchange gives us this equation. If we compare these two equations, we find that here curl was to be done first and then time derivative, but here the order has changed. We have to take time derivative first, then we have to do the curl. Now here we have curl, here we have curl, of course with a negative sign. Then we can bring them to the same side and then take curl common to end up with this equation. Now use this vector identity which says that curl of grad of any scalar is 0. Now what will be that scalar? We can either take grad V or we can take grad of minus V, in other words minus grad V. Now we can make any of these two choices. Our personal choices are different, maybe widely varying, but in some cases we make the same choice. We have to make the same choice. For instance, wearing the same uniform in a school. Here too people make the choice of minus grad V. So as per convention, we too make this choice. So if we make this choice, we end up with this equation, and therefore here we have curl, here we have curl. So these two can be compared, and therefore we end up with this relation. So we have E equal to minus grad V minus del del T of vector A. Now this is a general result which is valid for non-stationary situation. Now in electrostatics we had E conservative, which led to E equal to minus grad V. The same result is obtained from here if there is no time variation, that is if A is explicitly time independent. If it does not contain time explicitly, then del A del T becomes 0 and we end up with E equal to minus grad V, the stationary situation result, and this is called electrostatic field. We therefore end up with this result. This is B equal to curl A, and this is E equal to minus grad V minus del A del T. Now this relation represents the fact that E and B are derived from the potentials A and V. This means that if we shift the potentials, that is if we start with a different set, say A prime and V prime, we'll end up with a different field, say E prime and B prime. Now in this problem, the special choices that we were asked to make was A plus grad of gamma and V minus del del T of gamma. So we can make these choices here, and therefore we can rewrite this with this set of potentials. And if we do that, the value of E turns out to be this one, and this part is just E. This E is here reproduced, and this part cancels out because here again two operations are involved in these two terms, and since space derivative and time derivative, they can be interchanged, they cancel out. So what we have is actually E prime is equal to E, and this part is easier. Vector B prime is curl of, in this case, A prime, and A prime is actually this one. So we have A plus grad of gamma here coming in, and this gives us curl of A, which is actually B, and we have curl grad gamma, which is 0. Curl grad is 0. Therefore we end up with the same B. So we get the same fields E and B even if we start with two different sets of potentials. This means fields are invariant. Let us show it here through this diagram. So this is the set A and V, and this is another set A plus grad gamma V minus del del T of gamma, and if we move from this set to that set or the reverse way, what we are doing is we are making a transformation. This is called gauge transformation. Now this transformation does not affect the field values because this set gives us the same field as this one gives. So we say that fields, that is E and B, are gauge invariant. They are invariant under gauge transformation. We'll end up with a final problem. This is the problem, the last problem we will deal with in this lecture. There are four values of potentials given, A, B and C and D, and we have to choose that potential which does not give a magnetic induction pointing along k hat or z direction. So in other words, which of these four gives a magnetic induction not pointing along z direction? Now we use this definition B equal to curl A, and this is the explicit form written in Cartesian coordinates of B in terms of A. Here are the components, and we can see the options. There are four options, and this is AX, this is AY, AZ. Similarly, we have AX, AY and AZ and so on. Now B should not be along K cap, so the K component or Z component should vanish. Now the Z component is del del X of AY minus del del Y of AX. So this one should be 0. In other words, these two should be equal. Now we can just have a check. So this is the required condition. If you start with option A, we find that this condition is not satisfied. Option B satisfies this condition, and C and D does not satisfy. You can just have a glimpse of it. So option B is the correct answer, because here we have del del X of AY and del del Y of AX both being B0 by 2. So the answer will be option B. Now let us extend this problem a bit further. We have four values of A. Let us find the corresponding B fields that are generated by this vector potential. So we have extended the problem. Let us find B in the four cases, and this is the equation which we can employ. Now the first A is this one, which is actually minus B0y into I hat, and B equal to curl A takes this form. Instead of AX we put this value, and here we have J cap component 0, K cap component 0, and if you open up this determinant we end up with K cap B0. Option B gives us A which is of this value, and this gives a vector B which is 0. So this is not along K cap, this is actually 0, not along K cap, so this was the answer actually. In case of option C, we had A of this value, and this gives us this amount of B, and the final one gives k cap b0. Now here one thing is to be noted, that all the three options A, C and D, if the calculations are correct, give the same B, k cap b0, k cap b0 and k cap b0. So in view of this, we can extend the problem further. Let us extend the problem. We see that vector A equal to minus b0 y I cap. This was the first option. This one was option C, and let us call it A prime. Now both lead to the same magnetic induction. So this means from this potential, even if you shift to this potential, B is same. So we can ask, what is the transformation that connects this A with this A? And this transformation is called gauge transformation. Now vector A and vector A plus grad gamma both lead to the same B, k cap b0 in this problem. Now the problem is to find this gamma. So clearly, let us start with this expression. A prime is A plus grad of gamma. Now the value of A prime is put here. A, the value of A is here. We have put it, and grad of gamma, we do not know gamma. So we have this equation and we can easily solve it. So we can write it in this way. Grad gamma can be expanded, and then we can compare, and finally simple calculation gives us gamma. And we have done these things in mathematical physics class, the technique of calculation of partial differentiation. So we end up with this gamma. Now lastly, let us check whether the gamma we obtained is correct or not. So let us check it. Let us start with A prime equal to A plus grad of gamma, and the value of A prime was this thing. We are not taking it now, we are deriving it from this expression. So instead of A we have put this value, so this is written, and instead of gamma we have put this expression, and then simple calculation gives us this value, and this is actually this one. So these two expressions match. So this means our calculations are right. So what we have done here is, we started with one A, made a gauge transformation, shifted to another A. The mode of shift was through this grad of gamma, where gamma is b0 by 2 xy plus some constant c. So even if we shift or transform vector A by this amount, magnetic induction remains invariant, gauge invariant. Let me end this lecture with a quote from an American inspirational speaker and author, Esther Hicks. The law of attraction is most understood when you see yourself as a magnet, getting more and more of the way you feel. In reality, we have to experience both attraction and affinity, as well as repulsion and rejection, and we have to live with it like a magnet. Thank you.